Hello there, AP Environmental Science class. Welcome back to this will be part two of my lecture on Chapter 13, Non-Renewable Energy. In part one, we spoke about oil, and we spoke about natural gas. So now we're going to transition, and in this part, we're going to begin talking about coal. So what are the advantages and disadvantages of coal? What we're going to learn is that coal has a high net energy yield, but unfortunately is very, very dirty. And this is what we'll begin to discuss kind of the morality around using coal. Again, how can you tell a country that's trying to industrialize that you can't use coal because it's plentiful, has a high net energy yield, has a very low cost? How can you tell them you can't use this because it is so dirty for the environment? Well, while we're here in America, 1800s, early 1900s, that's what we used, right? Really, it's been in the past 40 to 50 years that we've kind of began to phase out coal here in the United States. So conventional coal is plentiful. All right, it's all over the place. It has a high net energy yield and it has a very low cost. However, using it has a high environmental impact. And again, this is what we're going to talk about over the course of the next couple of slides. We can produce gaseous and liquid fuels from coal. We'll talk a little bit about that. However, the net energy yields are a little lower and they actually have higher environmental impacts than conventional coal. So again, maybe not necessarily the way to go here. But again, we'll discuss it all. So here are the advantages and disadvantages of coal. Again, the advantages on the left here: ample supplies in many countries. Again, medium to high net energy yield, a low cost when environmental costs are not included. Disadvantages: severe land disruption and water pollution to get the coal out of the ground. Fine particle and toxic mercury emissions threaten human health. And coal emits large amounts of carbon dioxide and other air pollutants when it is produced and burned. So again, very efficient, very cheap, but very, very dirty when it comes to the environment. Coal. Coal is a plentiful but dirty fuel. Coal, solid fossil fuel formed from the remains of land plants. All right, so that's where coal comes from. And again, it is non-renewable because it takes millions of years to form. It is burned in power plants. In 2015, coal generated 40% of the world's electricity. Again, not so much here in the U.S. these days, even though we still have some coal-fired plants. We're definitely, in other countries, especially underdeveloped countries, this is where they're getting their electricity from. Largest consumers of coal: China, the United States, and India. Okay, so what's the environmental cost of burning coal? Well, mining coal severely degrades the land. Okay. Again, you got to pull this stuff out of the ground, so it severely degrades the area that you are mining. You have water and air pollution, right? Soot, that's those fine particles that are left over from when coal burns, coming out of those smokestacks, and of course carbon dioxide. In addition, coal produces trace amounts of mercury and other radioactive materials that then go into the atmosphere. Now, we do have scrubbers, which remove some pollutants before they leave smokestacks. These scrubbers are in the smokestacks, which will try to get some clean out some of the pollutants, but unfortunately this then produces a coal ash that must be safely stored, because while you're scrubbing all the pollutants out of the smokestack before the coal smoke leaves the power plant or whatever you happen to be industrial whatever happens to be burning the coal, right? You still have the leftover. You still have the leftover pollutants that you got to do something with, right? So then that's what's known as coal ash, and that still has to be safely stored somewhere. So this is actually the different types of coal. Believe it or not, there are different types of coal that actually has formed. You'll notice to the left is increasing moisture content, while the right has increasing heat and carbon content. So something called peat, which is actually not coal, but it's kind of like coal. It's partially decayed plant matter in swamps and bogs, and you can actually burn this. So those folks in northern Scotland and Ireland actually still do this to this day. They'll go into these peat bogs and they'll cut out the peat out of the ground, and they'll carry it home, and then they'll actually burn it. You add a little bit more heat and pressure, and then we have something called brown coal. This has a low heat content, low sulfur content, so a little bit cleaner, but limited supplies, however, of this brown coal. Then you have bituminous coal, which we call soft coal. This is extensively used as a fuel because of its high heat content and large supplies, but it normally has a high sulfur content. So again, now you're releasing a lot of sulfur into the air when you burn this bituminous coal or soft coal. And then we have something called anthracite or hard coal. This is highly desirable fuel because of its high heat content and low sulfur content. However, the supplies are limited in most areas. So anthracite coal is a little cleaner than the bituminous coal, but again, we don't have as much of it. So what do we have the most of? We have the most of this soft coal known as the bituminous coal, but again, very, very dirty, as it has a high sulfur content and a high content of some of those other trace toxic chemicals as well. All right. So again, here are kind of the different types of coal here. Just understand them. What we're looking at here, all right, is the carbon dioxide emissions as a percentage of the emissions released by burning coal directly. So coal-fired electricity, you're actually putting 286%. So it's an extreme amount. It's percentage of emissions released by burning the coal directly. So it's more than 100% there for that coal-fired electricity. That's how much carbon dioxide we are putting into the atmosphere. There's your synthetic oil and gas production from coal, 150%, right? Coal itself, 100. So again, if you're just burning coal, there's the 100%. That's where the difference is. So obviously, coal-fired electricity produces so much more carbon dioxide than just burning coal itself. Synthetic oil and gas produced from coal, right? More percentage of carbon dioxide emitted than just by burning coal. You'll notice the tar sands, the oil, the natural gas. We've already talked about that. A little bit less of pollutants there. You'll notice natural gas, only about 58% of the carbon emissions compared to burning coal. And then we'll be talking about nuclear power in just a couple of slides. Geothermal actually will be in the renewable energy section, which will be another chapter, but you'll notice much, much cleaner when it comes to the carbon dioxide emission. So again, this is why we need to kind of move away from producing our electricity with coal, because it is just destroying the environment. Again, 286% of carbon dioxide emissions when you're making electricity from coal compared to just burning coal itself. Okay, so again, we need to migrate away from coal. And one way to do that potentially, again, is that full cost pricing that we talk about a lot in this course. We are not paying the full cost of using coal. Harmful environmental and health costs are not included in the market price of coal-generated electricity. If it was, that coal-generated electricity would be so expensive that people would not want it and they would try to find alternatives. But we're not producing or not providing a full cost price here to coal. We're not putting in the environmental effects, and as a result, coal is rather cheap. How can we implement full cost pricing on coal? Well, phase out subsidies and tax breaks, require stricter air pollution control, tax the CO2 emissions, right? If you tax the amount of carbon dioxide you put into the air, coal-fired electric plants, right, 286%, they would definitely try to lower that and regulate that coal ash as a hazardous waste, because right now it's not regulated as a hazardous waste. So what is the future of coal? Well, U.S. coal usage dropped 18% between 2007 and 2013, increased competition from natural gas, wind, solar, and also from a grassroots political opposition. Again, really for the last 20 to 30 years, we've been trying to phase out coal here in this country because, again, we know how dirty it is. Natural gas should overtake coal as the largest electricity source here in the U.S. By the 2030, so next decade, which is good. U.S. coal producers are exporting the coal, so we are now using it. We're exporting to India, Africa, and Asia. And again, here's those issues. These now developing countries, right? They're about 150 years behind us. We were using coal 150 years ago. Now these countries want to use coal. And now here's the issue, right? Because we're finding out coal is so bad for the environment. But again, how do you tell these developing countries you can't use this cheap form of electricity to provide for your people? Again, this is the moral dilemma we talk about a lot in this environmental science course. So We can convert coal into gaseous and liquid fuels. Conversion of solid coal into what's known as synfuels, synthetic natural gas, SNG, by coal gasification, or methanol or synthetic gasoline by coal liquefaction. Producing synfuels, though, requires mining 50% more coal, and you get a lower net energy and cost more to produce than coal. So not exactly sure this is the way to go. Just understand that there are these synthetic ways to convert coal into gaseous and liquid fuels. But again, the net energy is lower. Because it basically costs more to produce than coal. So that, of course, lowers the net energy, and you actually need 50% more coal. So now that's going to increase the mining that is needed, and that will increase the degradation of the land in that area. So again, kind of a lose-lose situation when you talk about these synthetic fuels. What are some advantages? Large potential supplies in many countries. Vehicle fuel can be used for vehicle fuel instead of using oil, and lower air pollution than coal, but not much lower. Disadvantages: low to medium net energy. Again, requires mining 50% more coal with that increased land disturbance, water pollution, and water use. And there's higher carbon dioxide emissions than coal. So lower air pollution means there may not be as many of those particles, right? That coal kind of ash, that those particulates in the sky with the synthetic coal, but you actually have higher carbon dioxide emissions. So at the end of the day, probably not the way to go, but just understand what these synthetic fuels are all about. All right, so that is coal. We now move on to nuclear power. All right, so again, as always, there are advantages and disadvantages to this. So nuclear power has a low environmental impact and actually a very low accident risk, right? All you hear about with nuclear power is when there is a meltdown or some kind of accident. But really, if you look at the statistics, the chance for an accident with nuclear power is actually very, very low. What are the drawbacks? Low net energy yield, because it costs a lot of money to produce nuclear power. Again, high cost. There are the fear of accidents. We do have some long-lived radioactive waste that we need to talk about, and the role in the spread of the nuclear weapons technology, also kind of a drawback from nuclear power, because the same way we can create electricity with nuclear power, you can create bombs to kill people. So again, nuclear power has gotten a bad name because of some of these drawbacks. So how does a nuclear fission reactor work? Well, controlled nuclear fission reaction occurs in a reactor. So again, just to remind us, nuclear fusion, which is what happens in the sun, is when two lighter elements fuse together to form a heavier element, energy is released. Nuclear fission is the opposite of that. This is when heavier and heavier element is ripped apart into two lighter elements. Energy is then released as well. And actually, much more energy is released via nuclear fission as compared to nuclear fusion. So we have light water reactors, which basically boil water to produce steam to spin a turbine. So again, you have this nuclear fission happening that produces energy, which is basically heat that boils water, produces steam that spins a turbine, and then that turbine actually produces the electricity that then is used. Nuclear power plants are fueled by uranium ore mined from the Earth's crust. Enriched uranium packed as pellets into fuel rods and to fuel assemblies. And again, the uranium then is ripped apart, and that's what the nuclear fission is all about. And then the control rods will absorb the neutrons coming out as the uranium is pulled apart. Water is the usual coolant in a nuclear fission reactor. The containment shell then you have around the core for protection. The problem is that containment shell breaks, that's when you have nuclear radioactive material then leaking out into the environment. There's an emergency core cooling system just in case there is an issue. Typical cost to construct, $9 to $11 billion, right? So this is why they have such a low net energy yield, is because the upfront costs so much, so great to construct a nuclear power plant. United States, France, and Russia, the leading producers of nuclear power in 2014. All right, so again, how is this nuclear fission working? Basically, you have uranium-235. It is crushed hit with a neutron that then fragments that that element, right? That atom into smaller atoms with less mass, basically, and that releases a lot of energy, and then that process continues on and on and on. All right, that's basically how a nuclear fission reactor works. And again, what are we looking here? Again, more of what we're looking at with this nuclear fission reactor. I have seen some test questions where they do ask you to kind of explain how this happens, how nuclear fission reactors work. So definitely understand a little bit about what's going on this page. Again, we have the cool water input that comes in here. All right. This is where you're getting, actually over here is where you have your control rods, right, that produce the fuel. You have hot coolant that then goes into here. This then produces steam, right, that goes into here to run the turbine, which then goes into a generator, which then the useful electrical energy is put out. What then do we have? We have hot water that is then put into these cylinders. Some of the hot water is returned, but a lot of it is actually pumped out into whatever body of water happens to be there that then pulls in the cool water input. This is one of the issues with the Indian Point nuclear power plant. What happens is you put a lot of hot water into the Hudson River. The Hudson River isn't used to being that hot, and so you basically have an issue right around the nuclear power plant where you have aquatic ecosystems can have some trouble because, again, they may not be used to the heat, and now you are putting in this artificial heat, this artificial water back in. Again, that's the leftover water from the reaction that produces the steam that runs that turbine. This is the key, though, here, guys. Look about this. Useful electrical energy, only about 35%. That means about 65% of the energy is wasted. This is another issue with nuclear fission reactors and why they have that low net energy yield. They're not very energy efficient, okay? Most of the energy, 65%, which is that heat, is lost to the environment, right? Either going out, waste heat, you'll notice it right here, or that hot water output that goes into the body of water that's next to the nuclear power plant. Again, you're wasting that heat, you're wasting that energy. So it's not very energy efficient, unfortunately, nuclear power, and this is yet another reason why it gets a little bit of a bad rap. It's very expensive initially, and it's not very energy efficient. So what is the nuclear fuel cycle, right? So first we need to mine that uranium that we're going to use in the fission reactor. We need to process and enrich the uranium to make fuel. We then use it in the reactor. We then need to safely store the radioactive waste, right? So after all those neutrons bombard the uranium atoms and they split up and they release energy, you're going to have some of these atoms, some of these particles left over. They're radioactive, and now we have to store them somewhere. Retiring the worn out plant also takes a lot because when you have to decommission these plants, it costs a lot of money because you have to store its high and moderate level radioactive parts somewhere. You basically need to store, if you break down a nuclear power plant, you need to store every bit of it somewhere because every bit of it it has some form of radioactive material in it, right? So now we got to figure out where do we store all of this radioactive material, leftovers, coming from that nuclear reactor. So here is the nuclear fuel cycle. So again, here we are. We're mining, mining that uranium, enriching it, right? Then sending it to the fuel assemblies, the reactor, where then you get the temporary storage, some underwater cast or in dry cast, and then some kind of permanent storage somewhere underground. What you see in the dotted lines, there is some recycling that is trying to be done here. Some of these fuel rods are recycled a little bit. Again, decommissioning of the reactor, you have to store everything underground. All right, so just kind of understand the general fuel cycle here when it comes to nuclear fuel, because again, these are some of the issues with nuclear fuel. Again, we have to store this radioactive material. So conventional nuclear fuel cycle, advantages, disadvantages, our favorite charts here. Advantage, low environmental impact. Again, if we don't have the accidents, emits 1/6 as much carbon dioxide as coal, right? So much cleaner and low risk of accidents in modern plants. Disadvantages, low net energy because of that high overall cost, produces long-lived harmful radioactive waste that we have to deal with, and promotes the spread of nuclear weapons. I don't know how much that promotes the spread of it, but obviously the technology can be used to produce nuclear weapons as well. So how do we deal with the radioactive nuclear waste? Well, rods, those fuel rods, right, must be replaced every 3 to 4 years with new uranium in there, right? Because once every 3 to 4 years, the uranium that was in there has been bombarded and it basically has done its fission, and now it's you can't do it anymore. You can't get any more energy from it, so you have to replace it with more uranium, and you got to store it somewhere. So first, they store it in water-filled pools for several years to cool down. That's how long it takes to cool this stuff down. It's so hot. It takes several years. Then they transfer it to dry casks, where then it can be processed to remove some of the plutonium, which again is the leftover from the uranium. Reprocessing reduces storage time from 240,000 years to about 10,000 years. Costly, though, and produces materials that could be used in weapons. Again, though, reprocessing, reducing the storage time from 240,000 to 10,000, that's helping a little bit, but you still got to store it somewhere for 10,000 years. This is the problem with nuclear fuel. These wastes stay radioactive for tens of thousands, even hundreds of thousands of years. So they need to be stored where they will not be disturbed for that long amount of time. And this, again, becomes some of the issue because we don't really have a permanent, secure repository. There was a site in the Yucca Mountains in Nevada, but that was actually abandoned years ago. And again, retiring the nuclear plant's enormous cost because you have to, again, pretty much have to secure every part of the nuclear plant because every part has some form of radioactivity to it. So these are the issues, right? To me, it's a very clean fuel. You can produce a lot of it. But again, what do we do with the waste? Where do we store it? And the costs are enormous right now. So unfortunately, the net energy yield ends up being rather low because of all of that. However, can nuclear power slow climate change? Well, nuclear power plants have no carbon dioxide emission, and the nuclear fuel cycle does emit some carbon dioxide right in the making of the fuel in the entire cycle, but 1/6 that of coal, so much less. Cutting global carbon dioxide emissions in half between 2015 and 2040 and meeting energy needs would require building 12,000 nuclear power reactors. This is according to Mark Linus, who's a climate change author. The moral of the story here, that's not possible. Okay, so basically, while we thought nuclear power was going to be the key here, when you actually do the nitty-gritty, you would need so many nuclear power plants to actually begin to cut those carbon dioxide emissions that at the end of the day, at least right now, it's not cost effective and it's maybe not the way to go. And what we'll talk about is that renewable energy in another chapter, right? The wind, the solar, the water power, that's maybe where we need to be heading to sustain ourselves over the next 100, 200, 300 years, etc. So controversy about the future of nuclear power. Again, nuclear reactors produce 19% of U.S. energy in 2014. 67 new nuclear reactors were under construction worldwide in 2015. U.S. government does provide subsidies, tax breaks, and insurance for the nuclear industry. However, accidents have dampened public confidence in nuclear power to the point that the Indian Point power plant just north of here actually has been now shut down. So again, we're kind of seeing a turn maybe against nuclear power currently. We'll see how that goes. Again, some new technologies, though, may be able to help. Advanced light water reactors that have built-in safety features. Smaller module light rate reactors. They're not yet built and evaluated, but they could potentially be moved around to different areas because they'd be small and modular. And then there's something called thorium-based reactors, which are less costly and a little safer. But again, we don't have many of them as we don't have a lot of that technology. So some solutions: reactors must be built so that a runaway chain reaction is impossible. That's your nuclear meltdown. Reactor fuel and methods of fuel enrichment and fuel reprocessing must be such that they cannot be used to make nuclear weapons. Spent fuel and dismantled plants must be easy to dispose of without burdening future generations with harmful radioactive waste. Taking the entire fuel cycle into account, nuclear power must generate a net energy high enough So that does not need government subsidies, tax breaks, or loans to compete. Right now, that's not happening per se. And its entire fuel cycle must generate fewer greenhouse gases than the other alternatives. All right. So this is what needs to happen if we are going to see nuclear power increase over the next coming years. All right, so a quick case study, the Fukushima nuclear power plant accident. This happened in March 11th, 2011. This was triggered by a major offshore earthquake and a resulting tsunami that came in and basically flooded out the power plant and caused it to basically have some major issues, have a basic meltdown. Important effect, it increased the fear about nuclear power. It revealed a single accident can cost over $500 billion, which this one did. Some countries, again, announced phasing out their nuclear power after this accident, and this has spurred Japan to actually reduce its energy use. So, again, these were the effects, and since then, we've kind of seen nuclear power maybe take a little bit of dip in the public perception. Again, we'll see how that goes down the road. Now, is nuclear fusion maybe the answer? So again, our power plants are fission plants where uranium is ripped apart, but maybe fusion's the way. So this is, again, two isotopes fused together to form a heavier nucleus or a heavier atom. This does release energy. And this is the technology used by the sun. Again, the sun uses fusion, not fission. However, the technology is very difficult to develop. No approach has produced more energy than it has used. So right now, nuclear fusion, we haven't been able to figure it out. But again, maybe that's something someone in this class watching this lecture right now, maybe you'll be the person who's able to figure this out one day. And maybe this will be the saving grace for us when it comes to energy. All right, so we're almost done. Just a couple of slides here, finishing up the chapter. Some big ideas, net energy. All right, that key factor in evaluating the long-term usefulness of any energy resource. We want that high net energy yield as compared to the low net energy yield. Conventional oil, natural gas, and coal, plentiful with moderate to high net energy yields, but they have high environmental impact by using not only pollution, but also degradation of land as you get this stuff out of the ground. Nuclear power life cycle, low environmental impact, very low accident risk, but high cost, low net energy. We have that long-lived radioactive waste we got to deal with, and again, did play a role in spreading nuclear technology. So last one, tying it all together, fracking, non-renewable energy, and sustainability. Again, horizontal drilling and fracking have greatly increased oil and natural gas production in the U.S. Long-term usefulness of an energy resource depends on its net energy. Is it high or low? And what's our challenge? Find ways to reduce harmful environmental impacts of fossil fuels and nuclear energy. Option: shift to more renewable energy resources, and that's something we will talk about down the road. All right, so that concludes part 2 of my lecture on chapter 14, non-renewable energy. And as always, thanks for listening.